Let's take a look at a related rates problem involving a cone because the AP absolutely loves cones. The volume V of a cone, and the volume is given by 1/3 pi r squared h, is increasing at a rate of 28 pi cubic units per second. At the instant when the radius r of the cone is 3 units, its volume is 12 pi cubic units, and the radius is increasing at 0.5 units per second. Part A. At the instant when the radius of the cone is 3 units, what is the rate of change of the area of its base? Well, for this particular problem, we don't even need the volume of the cone because we're asked to find the rate of change of the area of its base. Now, if this is our cone and we have a circular base to our cone, we know what the area of a circle is. The area of a circle is just pi r squared. Now, let's think about all of the different things that are going to come out of this if we take the derivative. If we take the derivative of a with respect to t, then we get dA dt. Well, that's the rate of change of the area. We actually have not been given the rate of change of the area. However, we're asked to find it. So that's actually a-okay. We'll do that just fine. Now, if we take the derivative of r squared, we end up with 2r dr dt. There's an r and a dr dt in there. Now let's make sure that they've given us both of those bits of information. Let's see. Oh, r is 3, and the radius is increasing at 0.5 units per second. Well, that's dr dt. They gave us all the information that we actually need to know. So let's take the derivative. The derivative of a with respect to t is dA dt. This is equal to 2 pi r times dr dt by using the chain rule here. Now let's plug in our information. We have 2 times pi times the radius, which they told us was 3, and we know that the radius is increasing at a rate of 0.5 units per second, which means that dr dt is positive 0.5. And now we have 2 times 3 is 6 times 1/2 is 3. This is equal to 3 pi. Now let's take a look at our units. The area is going to be in terms of units squared, or square units, and time is in terms of seconds in this problem. So here's the answer. The area is increasing, because this is positive, the area is increasing at a rate of 3 pi units squared per second. Of course, that's referring to the area of the base at that particular moment. Part B. At the instant when the radius of the cone is 3 units, what is the rate of change of its height, h? Alright, well, let's get down and dirty and let's just start doing this thing. Here we go. We've got the volume of our cone is equal to 1/3 pi r squared h. Now, we have 3 variables here, v, r, h, and they're all in terms of t, so these are all functions of t, which means that we have to use the chain rule for all of them. Furthermore, we also have this nasty product rule going on with r squared times h, and we've got some constant outside the product rule, so there's a lot of stuff going on here. Let's take a look. The derivative of v with respect to t is dv dt. Let's pull out that constant using constant rule. Here we have 1/3 pi times the derivative of r squared times h, and for this we have to use product rule. Well, let's take the derivative of the first. The derivative of r squared is 2r dr dt times the second, which is h, plus the first, which is r squared, times the second, which is dh dt. Now, we are trying to solve for the rate of change of the height, h, that is dh dt. So in this formula is given what we're trying to solve for. Now let's go through everything else and let's see if we can start just plugging things in. Well, first of all, dv dt, that's the rate of change of my volume. That's increasing at a rate of 28 pi cubic units per second. So I can just plug 28 pi in for dv dt. Let's put pi over 3 here. times 2 times r times dr dt times h. Well, r is 3 units, and we know that when the radius is 3 units, the radius is increasing at a rate of 0.5 units per second, so we know that r is 3, dr dt is 1/2, and h, they have not given us an h. That is interesting. We'll have to take a look at that in just a moment. So 2r is 3, and dr dt is increasing, so it's positive 1/2 times, we'll just leave a little h right here, plus r squared, well, that's 3 squared is 9, times dh dt. Alright, let's clean this up a little bit. Here we have 28 pi is equal to 2 times 3 is 6 times 1/2 is 3 times h is 3h. And let's distribute this pi over 3 right here. So 3h times pi over 3 is just pi h. And then 9 dh dt times pi over 3 is 3 pi dh dt. So really, to solve for dh dt, all we need now is to find h. Let's see if we have any information that could help us solve. Oh, yes, we do. We have the volume of a cone. That will help us actually kind of nicely, because we know that at this particular moment, its volume is 12 pi. We also know at this moment that the radius is 3. So times 9 times h. This is going to give us what we need. We can solve for h using the volume formula for a cone. 1/3 times h times 9 is 3 pi h. So here we have 12 pi is equal to 3 pi h. We can divide both sides by 3 pi, and this yields that h is equal to 4. Well, we can now use this fact down below. Here we go. H is equal to 4, so that means that 28 pi is equal to 4 pi plus 3 pi dh dt. Let's subtract 4 pi from both sides. 28 pi minus 4 pi, that is 24 pi, and that's equal to 3 pi dh over dt. And now let's divide both sides by 3 pi, and this yields that dh dt, or the rate of change of the height, is equal to 8. H is in units, and t is in centimeters. So the height is increasing at a rate of 8 units per centimeter. And finally, part C. At the instant when the radius of the cone is 3 units, what is the instantaneous rate of change of the area of its base with respect to its height, h? Now, this isn't necessarily a related rates problem. However, this is the kind of thing that the AP will give you as the last part of a related rates problem. And you have to use all of the information that you found before to be able to solve it. I call these algebra death problems. Now, I call that because you just have to plug through and see what happens. So we are asked to solve for the instantaneous rate of change of the area of its base, that's dA. However, it's with respect to its height, h. Well, that's dA dH. Now let's see, in part A, we found dA dt. And in part B, we found dH dt. So somehow we're going to have to use all of this information to come up with a method or a model of solving for dA dH. And in fact, if you remember chain rule, one of the definitions of chain rule is this exact thing. It says that dA dt is equal to dA dH times dH dt. Or in other words, the derivative of the area with respect to stuff times the derivative of the stuff with respect to time. So we're using h as the stuff, the go-between, to put the dA dt together. Another way of thinking about this is, look, DH's, they cancel out. Gone. Boom, boom. Okay. Well, dA dt, way back in part A we found, was 3 pi units squared per second. We're solving for dA dH, and this is multiplied by dH dt, which we found in part B is 8 units per second. This means that dA dH is equal to 3 pi over 8. Now let's think about the units here. A is my area, that's in terms of units squared. And H, that's my height, that's in terms of units. Well, units squared divided by units is just units. So the derivative of my area with respect to height is given by 3 pi over 8 units. And that right there is the answer. Thank you for watching.